what's known as Newtonian physics. A lot of it is coming from these chapters, the sort of physics, the mathematics that we need. Anyway, so we were discussing car versus SUV. Both of them are going 60 miles per hour. They will lock up their brakes at the same time. Neither is an anti-lock brake system, right? So the question is, which one is going to come to a stop sooner? Now, most of you guys said it's the car. All right, you can make that argument. Most of you guys will argue that the car will come to a stop sooner because it's lighter, right? It's lighter, less force is going to be required. Okay, the reason why the car is coming to a stop, just remember this, guys, because of friction. And surface friction is dependent on or sensitive to weight. All right, so which means that the lighter vehicle is going to experience less friction. Heavier vehicle is going to experience more friction. There are people who will argue with you, especially the SUV owners. They will argue that their SUVs will come to a stop sooner because they're heavier, they will experience more friction. All right, so most of you guys will make the argument that the lighter car is going to come to a stop sooner because it's lighter, it's less inertia, which means that's going to require less force.
There's no question four-wheel drive vehicles offer better traction in the snow and can get through bad weather conditions when other cars cannot. But there is one thing, they do not necessarily do better than any other vehicle. What is the biggest mistake that SUV drivers make in bad weather?
Underestimating the stopping distance.
Some motorists assume since they have four-wheel drive, their SUV will stop quicker. Can an SUV stop better in bad conditions than, say, a Honda Accord?
Absolutely not. In fact, even on dry pavement, an SUV takes longer to stop than an ordinary car would.
Because of the weight of the vehicle, does it take longer for it to stop?
Oh, yes, absolutely. The heavier the vehicle, the longer it takes to stop.
All right, so that's the commonsensical approach. Most of you guys will agree with what he said. The next observation was, once again, you have two cars, one with the anti-lock brake system, the other without. So which one comes to a stop sooner? The one without the anti-lock brake system will skid to a stop. So if it's going at 60, you lock up the brakes, you will go into a skid right away, guys. It's going to slide. It's going to skid. The one with the anti-lock brake system is going to roll to a stop, which means that it's going to come to a stop without skidding. All right, so which one comes to a stop sooner? You guys were kind of split on this one. It was 50-50. So we got a car versus a train, right? So the train is going at 60, the car is going at 60. So both will lock up their brakes at the same time. Both will lock up their brakes at the same time. So the question is, which one comes to a stop sooner? All right, this one is the easiest one because you already know the answer for this one. You know the train is going to take a lot longer to come to a stop.
Consider this. A fully loaded freight going 60 miles an hour might take 1.5 miles to come to a halt after the brakes are applied.
Now, is that even realistic? Do you think it's going to take 1.5 miles?
That's the length of...
If it's fully loaded freight, you're thinking, yeah, because this thing's probably going to weigh millions of pounds. You know, that's inertia, right? So it's going to take forever to stop it.
25 football fields.
All right, so whenever we walk, drive, whenever we get around, we get to speed up, slow down, change direction at will, guys, which implies that there's an external force acting on it. So the question is, where does the external force come from? It comes from the action and reaction forces. Through action force, you apply a force on the ground via friction, and the surface is going to apply the same force back on in the forward direction via friction. All right, once again, you apply a force on the ground in the backward direction through friction, and then the reaction force is going to act on you in the forward direction, once again, through friction. So that's what happens. If it weren't for friction, you can't walk, you can't get around. All right, you would be stuck at the same spot forever and ever and ever.
Of how it works. Look at this video from ITT Automotive.
All right, so speaking of friction,
a company that manufactures ABS systems. First, watch what can happen without ABS.
All right, so without the anti-lock brakes, tough to control the car, isn't it?
Then, with ABS.
With the anti-lock brake system, the same car, same driver, same speed.
Driver stops in time.
You'll control the car better.
And maintains control of the car.
It'll also come to a stop much sooner. All right, so what does the anti-lock brake system do? Increases the friction, guys. Increases the friction. Anti-lock brake system simply by pump the brakes for you, increases the friction. So the frictional force goes up. The car comes to a stop soon. All right, so the question is, how does pump the brakes will increase the friction or help increase the friction? All right, so now we have to take a look at some contributing factors to the frictional force. Surface friction is going to come from the nature of the friction, so that matters. What else?
We are closed now for dry day.
Conditions of the surface are going to matter. Dry asphalt, wet, icy. All right, so the different conditions will give you different amounts of traction. All right, so this is known as the coefficient of friction, otherwise known as the traction number. When the surface is dry, you will get a certain amount of traction. As soon as it becomes wet, the traction changes. Weight is going to matter. We will call it the apparent weight. Surface area contact is not going to matter. All right, so the surface area contact is not going to matter. So just get rid of that. What matters is the coefficient of friction, which is mu, and the apparent weight. All right, so heavier something is, the more friction is going to experience for a given surface. All right, heavier something appears, the more friction is going to experience for a given surface. That's what it means. All right, so you get your friction from the amount of traction that the surface is going to provide, and you also get your friction from how much something weighs or appears to weigh.
Of how it works. Then, with...
All right, so let's focus on the anti-lock brake system. All right, so let's focus on the anti-lock brake system. I think we'll go over this. All right, so there are two types of friction. Static when the surface is not sliding, and kinetic when one surface is sliding over the other one, right? Just when it is at the verge of sliding, the amount of friction that this experiences, the static friction it's experiencing, is going to be larger than the sliding friction when it goes kinetic. All right, so static frictional force is going to be larger than kinetic frictional force. Maximum static frictional force is going to be larger than kinetic frictional force. Okay, so that's sort of an accurate statement. So the question is why? All right, so take a look at the rubber and concrete for a dry surface. Here's your static frictional force. That's coefficient of static friction, or the traction number. As soon as it starts to skid, it diminishes. It becomes smaller. All right. So this is the amount of traction that it's going to experience at the verge of skidding. And as soon as it goes into the skid, the traction goes down. That's what it means. All right. So the argument, you got two types of friction. You got static and kinetic. Static means they're at rest. Kinetic means one surface is sliding over the other one. They have the same formulas. Both of them are going to depend on the apparent weight, but both of them are also going to depend on the traction number. Here, the traction number is smaller. All right. So here, the traction number is going to be bigger. So the traction number is measured for the maximum static frictional force, which means that the maximum static frictional force is going to be larger than kinetic frictional force because its traction number, the coefficient of friction is actually larger. Coefficient of friction is actually larger. All right, guys, it's going to take a lot more force to get something moving than keeping it moving. So that's not only an experimental fact, but so real life experience. All right, so we discussed this before. Let's discuss it again because this is a good test question. All right, so this is a sliding tire. It's going to experience kinetic friction. This one is a rotating tire or rolling tire. It's going to experience static friction. Okay, so here's a question. Why is this one on the left experiencing kinetic friction? Short answer is take a look at the point of contact right here. Notice that the point of contact is sliding. All right, so one surface is sliding over the other one. So which means that in this case, the point of contact is sliding against the other surface. So this is sliding friction. This is kinetic friction. Yeah, this tire is rotating or rolling, but the point of contact is always at rest. Point of contact is always at rest, and that's the reason why this is a case of static friction. So this tire is always going to experience static friction. So the question is, how do you maximize that static friction? You maximize that static friction by using an anti-lock brake system.
Here's how a second, faster than you ever, up to 18 times a second.
So the anti-lock brake systems will lock up the brakes 18 times per second in order to maximize the average static frictional force. So they will lock up the brakes 18 times per second in order to maximize the average static frictional force. Imagine that you don't have an anti-lock brake system. Boom, what do? You lock up the brakes. All right, in panic, you want to stop, you lock up the brakes. Static frictional force is maximized, and then as soon as it's maximized, the car goes into a skid. So which means that static friction turns kinetic. Static friction turns kinetic. As soon as it turns kinetic, notice that the frictional force diminishes by this amount. So what that means is only this portion of the static frictional force is larger than your sliding friction. So more often you pump the brakes within this region, the higher the average static frictional force is going to become. All right, if you do 2 times per second, the average static frictional force is going to be here. If you do 5 times per second, notice that this region starts to diminish when you start to pump the brakes harder and harder, faster and faster, not harder. So what happens is the average static frictional force goes down. All right, so the same idea, you lock up the brakes, static frictional force is maximized. The moment it's maximized, it's going to go into a skid. That's what it means. All right. So the frictional force, sliding friction, is going to be smaller than this portion of the static frictional force. So this is the region within which you pump the brakes. So more often you pump the brakes within that region, the higher the average static frictional force is going to become. So this car will come to a stop sooner than the other one. That's it. So that was the main argument.
Don't be alarmed by the shuddering you'll feel with ABS brakes. That just tells you the system is working. If your car doesn't have ABS, that's when you do pump the brakes.
All right, the thing that I don't get regarding this one, you cannot pump the brakes more than once per second. I'm not entirely sure how much that's going to help. All right, we discussed these before. All right, car versus SUV. Which one is going to come to a stop sooner? All right, this is problem number 2 from the handout. Instead of using an SUV, I decided to use a mega truck. All right, so car is 2,000, mega truck is going to be 200,000, right? This thing is 100 times heavier, 200,000 kilograms of a mega truck. That's 500,000 pounds. So this sort of stuff does not exist in real life. This is way heavier than the heaviest truck on the road. All right, so both of them are going at 60 miles per hour. They will lock up their brakes. All right, so the kinetic friction is the only force acting. So this is the coefficient of kinetic friction. Do a force diagram first. Identify your forces. Frictional force is going to oppose motion. It's got weight, it's got normal force. That's it. So those are the only forces. This vehicle is going to skid to a stop along the next direction. While come to a stop. All right, so this is the distance it's going to take. This is the time it's going to take to come to a stop. All right, so this is problem number 2. So figure out the weight, the normal force, frictional force acting on it, the net force, the acceleration, the distance it will skid, and the time it's going to take for it to come to a stop. So the weight, the normal force, the frictional force, the net force, and then acceleration. All right, so the skid marks the distance is going to skid and the time. All right, so I broke the problem into smaller pieces. Weight is mg. We know the mass is, so just get the weight. All right, so this is still 10 times, this is still 100 times heavier. Okay, so what's the next one? Figure out the normal force. Normal force is the reaction force, the weight in this case. Sum of all the forces on the y direction. There's no acceleration on the y direction, which means that the normal force, the apparent weight, is the same as your actual weight. All right, so these weights become the apparent weights. The next one is the frictional force. It's going to be, this is kinetic friction. It's going to be mu sub k times n. You know your n. Mu coefficient of friction is 0.85. So you end up getting 17,000 here. It's going to be 1,700,000 there. So that's the amount of friction it's experiencing. Okay, guys, let's stop at this point. So if I were to ask you which one is going to come to a stop at this point, what would you say? The reason these vehicles will come to a stop is because of friction. All right, look at the amount of frictional force acting on the car. Look at the amount of frictional force acting on the truck. Which one experiences more friction? The truck does. In fact, the amount of friction that the truck is experiencing is about 100 times larger. All right, so truck is 100 times heavier, but the friction is 100 times larger. So which one do you think is going to come to a stop sooner? All right, all of a sudden you're thinking, hey, the car is going to come to a stop sooner. And all of a sudden, if you're looking at the numbers, you can't really justify that. All right, notice that the truck experiences 100 times more friction than a car does. And your argument all of a sudden seems very shaky. So we will continue. So what's the net force? We got to get the net force because net force is what causes acceleration. Net force is just sum up all the forces on the x direction. There's only one force acting, so it's the frictional force. So the net force is going to be the negative of the frictional force for both of them. All right, so we got the net forces. So where do you get the acceleration from? You get the acceleration from the net force. All right, so the net force divided by mass is going to give you the acceleration. All right, just for now, I want you guys to focus on this acceleration. Okay, ignore that one, just focus on this one. All right, now let's figure out the distance it's going to take for the car to skid. All right, so assuming that the acceleration is constant. All right, so we were looking for x. This got x in it, so it's this one. We don't know the time, so which means that this is the only one that we could use. So let's just grab that one. We know the initial speed. So this is the formula. Final speed is going to be 0. All right, so a little bit of algebra. So here's the final equation. Plug the numbers in. And so it's going to give us about 140 feet, I think. Okay, so it's 140. Okay, good. We got that. So it takes about 140 feet. All right, so the next question is the time, right? So how long would that take for it to come to a stop? So time. Okay, you can either use the first one because you know the distance, or you could use the second one because you know the final speed is going to be 0. All right, the first one is a quadratic equation because this is raised to the second power, requiring a quadratic formula. So it's doable, except it's a lot more mathematics. Work is a lot more involved. So I'll do the lazy thing, just pick the second one. All right, so final speed is 0. We're isolating t, so I'm just gonna let the symbol dance around for a while. That's called algebra. And then plug the numbers in. And then we end up getting almost 3 seconds. So it's 3.15 seconds, so it's 3 seconds. So what does it mean? What that means is the car is gonna take 140 feet and 3 seconds to come to a stop. All right. So if this car is going at 60 miles per hour, if you lock up the brakes, the car will skid. It's gonna skid 140 feet. Which means that you got 140 feet skid marks that you get to measure, in essence. How about the truck? The weird thing about this truck, a fictional truck, which is almost 500,000 pounds, it's so fictional that no such truck exists. Notice that this truck is about 100 times heavier, but the frictional force acting on it is 100 times larger. As a result, this truck is also going to have the same acceleration, guys. Acceleration is exactly the same as this. So what that means is this truck is also going to take 140 feet to come to a stop. It's also going to take roughly about 3 seconds for it to come to a stop. Counterintuitive. You didn't see this coming. Welcome to education, guys. Your common sense is no substitute for education. I'm going to be rubbing your noses in it until I'm done with you guys. All right. Which one comes to a stop sooner? Both at the same time. All right. It's going to take the same time and they will skid the same distance, provided that they're going at the same speed and they have nearly identical tires. That's it. Nearly identical tires. All right. You're just finding this out now, but this is no mystery for accident investigators. Imagine that you're driving in a 30-mile-per-hour zone at 60 miles per hour, and a kid runs in front of you out of nowhere. What do? You will apply the brakes, guys. You will lock up your brakes immediately. That's a reflex reaction. you will lock up your brakes. The car is going to go into a skid if you don't have an anti-lock brake system. It'll go into a skid immediately. All right. So you're going to go all the way up to the kid, over the kid. You're going to keep sliding for 140 feet. When the police shows up, what are you going to say? Hey, I was going too fast. The kid just came out of nowhere. I did the best I could. No, that's not what you're going to say. You're going to say, officer, I was going right at the speed limit. This kid came out of nowhere. All right. You could measure the skid marks. You could tell that I did the best that I could. They will measure the skid marks, guys. If it measures 140 feet, if they don't care that you're driving a Ford Tempo, they don't care that you're driving an SUV, BMW, truck, makes no difference. They'll know that you were going roughly about 60 miles per hour because the weight of your vehicle does not matter. Heavier the vehicle is, the larger the frictional force is. The weight goes up by 10 times, the frictional force goes up by 10 times. Weight goes up by 100 times, the frictional force goes up by 100 times. So it's not going to make any difference. All right, so
Can an SUV stop better in bad conditions than, say, a Honda Accord?
Absolutely not. In fact, even on dry pavement, an SUV takes longer to stop than an ordinary car would.
Because of the weight of the vehicle, does it take longer for it to stop?
Oh, yes, absolutely. The heavier the vehicle, the longer it takes to stop.
Who do you blame? I don't blame the guy. He's not an expert. They pulled him into the show pretending that he's an expert. This guy works for AAA, guys. He knows this stuff as much as a cab driver does. All right. Just because you know how to drive a car doesn't make you an expert physicist or an engineer. This is complete nonsense. All right. Dateline is at fault here. This guy is just feeding back your common sense and making you think that he knows what he's talking about. Absolutely not. This is complete garbage. All right. The way I did the problem, that was more of an illustration of, because I wanted you to discover something, because your common sense has been really loud in your head, because you guys always think that you know something, which is kind of cute. On the first couple of tests, the conceptual portions of the test, we discussed a lot of stuff during the lectures, and the conceptual portions of the test, I asked you the same questions, the stuff that we discussed. And then you guys are really good at selective listening, obviously, because that's what you guys are good at. It's a new generation. And then obviously this is being done online, so I can't see your faces, so I don't get to harass you as much as I normally would in person education, because I'd be yelling and screaming normally. All right. Yelling and screaming online doesn't really work. So forget that. But at the same time, you know, you get pre-lecture quizzes, the post-lecture quizzes and all that stuff. So it kind of forces you to pay more attention. But you guys are still doing it in a selective listening sort of way. You look at the topic, you go, oh, I know what we were discussing. I know the answer. No, you don't. I would never give you something that you can answer. This is not Disney. This is not grammar school. I'm not here to make you feel good. I'm here for you guys to get a good education, guys. And all of a sudden, because you weren't listening, you thought that you heard the correct answer as far as the correct answer is concerned, which one comes to stop sooner. It's the car. I'm telling you, 20-30% of you guys will still write down the car. All right. You will say the car will come to a stop sooner. As soon as you say that, I don't care what your explanation is. Out of 2 points, you will get 0.25. All right. Your explanation is wrong. Which one comes to a stop sooner? Both at the same time. Weight is not going to matter. The explanation that I'm looking for is because friction is what brings the car to a stop. Friction. Do you hear that? Friction. Friction depends on the weight. If the one vehicle is 10 times heavier than the other one, it's going to experience a force which is going to be comparable. It's going to be 10 times larger than the lighter one. So, which means that you increase the weight, the friction goes up, which means that the mass is not going to matter. Both of them will come to a stop at the same time. But from the computation we did, because I wanted you to discover that one step at a time, and all of a sudden there's a weird left turn that you don't see coming. So now that we've done it, let's clean up the algebra. The way we've done that problem is because I wanted you to discover something. I broke it down in a step-by-step fashion. This time, I'm not going to do that. I'm going to do it the way we would do it in physics. All right, so this is car versus an SUV. This is your problem number 3. Both of them are going at 60 miles per hour, guys. They will both come to a stop. All right, so the coefficient of friction, this is for the kinetic friction, because both of them will slide to a stop, skid to a stop. All right, so what's the distance and the time it's going to take for them to come to a stop? All right, I go to the formula sheet and grab a bunch of formulas that I think may be relevant to this case. The car is going to come to a stop. There's acceleration, which means that there's a force acting on the car. So everything that has force and acceleration are relevant. So those are the formulas I would grab. The next thing I'm going to do is I'm going to do a force diagram. All right, so you got a frictional force to the left, so it's going to be negative. W is in the downward direction, N is in the upward direction. All right, so this is the only thing which is required. The rest, the green stuff, is my own visualization purposes. So the car goes from initial speed to final speed within a certain distance, and boom, boom, boom. Okay, so the next thing I'm going to do is I'm just going to attack the problem. X is what I'm looking for. I usually take a direct approach. This formula has X in it. This formula has X in it. Assuming that the acceleration is constant, so those are the only 2 formulas that I could use, which means that the average acceleration formula, once I make that commitment, it's out of the picture. So the average acceleration formula can only be used if your acceleration is changing. All right, so for X, I'm thinking, should I use this? I don't know the time at this point, so the best one to use is going to be the last one. All right, so just grab this one and then start working it. All right, so final speed is 0, solve for x. All right, so you guys know how to do algebra at this point. So I'm just gonna let the symbols dance around for a while, follow the rules of algebra, and then we got the final equation. All right, so I know the initial speed. This is 60 miles per hour, expressed in terms of meters per second. Okay, I don't know what the acceleration is, but I know the acceleration is caused by an external force right here. And so the net force is what causes acceleration. So I can get the net force along the x direction. Along the x direction, which is this, it's going to be the negative of the frictional force. So net force is the negative of the frictional force. So back substitution. Now solve for A. Now do a back substitution again. All right, so the mass in the denominator becomes, in the numerator, negatives will cancel. All right, so that's my final equation. All right, so I got the, hold on. I got everything here. I got the mass, I know the initial speed. And do I know the frictional speed? Not the frictional speed, the frictional force, the frictional force. No, I don't know that. All right, so now come up with an expression for the frictional force. And so it's going to be apparent weight times the coefficient of friction. Now come up for an expression for the normal force. It's going to be from the y direction. So sum up the forces on the y direction. Notice that the acceleration is going to be 0 because this thing is not going to be moving up or down along the y direction. So which means that the apparent weight is the same as the actual weight. So do a back substitution here. And then do a back substitution there. All right, so now clean this up. We will get some cancellations. Masses will cancel. That's it. So the mass of the vehicle doesn't matter. All right, so this confirms the mass doesn't matter. So regarding how far the vehicle is going to skid, the mass doesn't matter. Okay, the only thing that really matters is the initial speed and the quality of the tires. That's it. How fast you're going and the quality of the tires. Vehicles with identical tires or nearly identical tires will skid the same distance. All right, so that's what it means. Mass of the vehicle is not going to matter because friction is proportional to the weight. Heavier the vehicle is, proportionally larger the friction is going to be. So for a given near identical quality of tires, the only thing that matters is the initial speed. All right, so plug the numbers in. It's going to give you, once again, 140 feet. Okay, guys, part B of this problem, make a note. Part B of this problem. All right, so part B of this problem is going to be your test question, or test question is going to be very similar to part B of this problem. All right, so just focus on it. So redo the problem. When you're doing the problem, solve for time. Okay, so that's what you need to do. All right, so next question. Which one is going to come to a stop sooner? Is it the train or is it the car? What do you guys think? Enjoy the confusion, guys. Which one comes to a stop sooner? Is it the train or is it the car? Okay, Victor, I'm going to give you 5 points for saying the wrong thing. Edward, I'm going to give you 10 points for saying the right thing. Edward says train is going to come to a stop sooner. And Jordan said both because the mass does not matter. Jordan, I'm going to give you 5 points for saying the wrong thing as well. All right, I'm going to go to Edward. Edward, you say the train is going to come to a stop sooner, right? Why? All right, so which one is going to come to a stop sooner, guys? Train is going to come to a stop sooner. Why? Mass doesn't matter, but which one comes to a stop sooner? It's going to be the train. Here's the reason why. All right, rubber on concrete. All right, so here's a skidding car. So the kinetic friction is 0.85. And steel on steel, notice that it's in 0.48. Okay, so coefficient of friction is not the same. All right, so concrete is going to give you, rubber on concrete is going to generate a lot more traction than steel on steel. All right, so which means that definitely, the train is going to, the car is going to come to a stop sooner. All right, yeah, it's the coefficient of friction. I would give yourself 5 points for that one. All right, in fact, let's continue with this one. Now, it's the same formula we will get to use. All right, so for the car, it's going to be 140 feet, right? Okay, now for the train, the coefficient of friction is going to be 0.48. And G is still going to be 10. It's still moving at 60 miles per hour. So let's take these and then plug those into that formula. And then we will get about 74 meters. Okay, so that's about 250 feet. All right, it's not a mile and a half. Okay, that number makes no sense whatsoever. All right, so the train is going to take longer to come to a stop. If it were to take a mile and a half, guys, these trains would be missing their stops most of the time. They would just take off and then start applying the brakes immediately. So that's just not the way to do it. All right, so it's going to take longer than a car to come to a stop, that's for sure. but it's not going to be mile and a half. That number is, once again,
If you were on the tracks in front of it, consider stop. If you were on the tracks in front of it, consider this. A fully loaded freight going 60 miles an hour might take a mile and a half.
Which means that it's written by someone who's aware that his or her understanding of physics is not there. It's just a guesswork.
Have to come
mile and a half, absolutely not. It's going to take almost double the distance of a car, but it's
to a halt after the brakes are applied. That's the length of 25-foot ball field.
All right, so that's not true. All right.
Today's cars brake better than ever, but it's up to your tires to track.
Your coefficient of friction for static and kinetic depends on the quality of your tires, guys. The numbers that we're using are average numbers.
Translate these advances into stopping power on the road. The Firestone FT70C uses Unity technology to help your car stop when the rain starts. So if you're not driving on FT70C tires with Unity, what's stopping you? The Firestone FT70C with Unity Ultimate Tire Technology, built to stop in the
better quality tires will help the company stop sooner. All right, so the coefficient of friction for static and kinetic cases will vary slightly, but obviously better quality tires will give you more traction, so there's no question about it.
Qualifying, the carefully balanced performance equation was swept away by the onslaught of rain. Wet track conditions meant the team's strategies for qualifying had to be completely reworked. New tires were rolled out. Normally, these cars use wide, treadless tires. The strategy being, the more rubber on the pavement, the better the grip. But the weather changed the priorities. Due to the rain, the team changed the tires with a deep tread, providing better traction in the wet conditions.
Okay, so there are a couple of things to
qualifying the carefully worked.
All right, so they go from treadless tires to the treaded tires.
Normally, these cars use wide, treadless.
What's the purpose of having treaded tires when it starts to rain? Does anybody know? All right, the purpose of using the treaded tires is so that you can channel the water away, right? That's the whole idea. They try to channel the water away. So the surfaces are still in contact with respect to each other. So you try to get the water away, so you make it deep enough so you can channel the water away. So instead of getting dry friction, you got a wet friction, but wet friction is still better than skating on water. All right, so that's what they try to avoid. Okay, now according to physics, and everything that I'm saying and defending and advocating comes right out of physics. These are the concepts, the details come out of these physics books. Okay, so according to physics, the surface area of contact does not matter. Given the fact that the surface area of contact doesn't matter in terms of how much it contributes to friction, why not just use regular treaded tires as opposed to using these treadless tires, if that's the case?
Tires. The strategy being, the more rubber on the pavement, the better the grip.
All right, so according to these guys, the more rubber on the concrete, the better the grip, which means that higher the traction is going to be. And physics will say, no, that cannot be true. So is it possible that these guys are completely clueless? All right, so these race car drivers and the race car drivers, do you think they don't know their physics? Do you think they don't know their stuff? The fact of the matter is, guys, these guys are knowledgeable and they hire the best of the best engineers and they have a lot of help from physicists and scientists. Okay. The problem is what's presented in the physics books. What's presented in the physics books is correct for smooth surfaces, just like this one. All right, notice that this is going to be sliding over the other one. You got one smooth surface here, you got a second smooth surface on top of it. In this case, the surface area contact is not going to matter. When it comes to tires, there's a contribution. Surface area contact is going to matter, except the contribution is marginal. All right, it's got a marginal contribution. If I'm driving a Ford Tempo, surface area contact is not going to make that much of a difference. These are race cars. These guys want every fraction of a second advantage over the other guy. Yeah, that's all you're going to get from that surface area contact. It has a very marginal contribution. In fact, it's so small that we would normally ignore it. These guys don't ignore it because they want every single advantage that they could get over the next guy. All right, so for all practical purposes, remember the surface area of contact is not going to matter. Your common sense will say it does matter. Once again, your common sense is marginally correct. The correctness of your common sense is so small that we will just ignore it. So it's actually wrong in that sense. All right, so bunch of problems. Okay, this chapter is all about the applications. How do you apply these concepts to different problems? Okay, so problem number 4. This one is kind of extra credit quality. I kind of like this one. Okay, because on the test, you guys get these extra credit problems. These extra credit problems are not necessarily complicated. It's just they're kind of cute. Let me put it this way. These are cute problems. So what's the maximum acceleration that a car can undergo if the static friction, coefficient of static friction is 1.2? All right, so how do you do a problem like this? So I got the coefficient of static friction. I want to know what the maximum acceleration that this car is going to undergo, right? I grab all the formulas related to acceleration. All right, and then I will do my force diagram. So what do we do? All right, so I want to generate a forward force in this direction. And then that's going to come from static friction. The reason it's going to come from static friction because the tire is going to apply a force on the ground in the backward direction. That's the action force. In turn, the ground is going to apply the same force back on the tires in the forward direction. That becomes the reaction force. So what drives the car is the static frictional force, guys. It's the static frictional force. All right, so the maximum acceleration that this is going to undergo is going to happen when you maximize the static frictional force, which means that at that point, the tires will start to spin. Okay, so what else do we have? We got the weight. Normal force is a reaction force to the weight. So those are all the forces that we got. All right, so acceleration is what I'm going to go after. So this formula is acceleration. So the net force on the x direction is what causes acceleration. The net force is the static frictional force. So we got that. Solve for A. So which means that divide both sides by the mass of the vehicle. Okay, now we're stuck because we don't know the mass of the vehicle is not given. So what do? Which means that we got to do more work. More than likely it's going to cancel. So we don't know the mass, we don't know the frictional force, static frictional force. But we have an expression for the static frictional force, which happens to be that. All right, so now we have the coefficient of friction, which is this, but we don't know what N is. And N is a reaction force right there. So it's a reaction force of weight. So sum up all the forces on the y direction. There's no acceleration on the y direction. And do a back substitution. And then do a back substitution again. Okay, guys, the masses cancel. And we're done. All right, so this is the maximum acceleration that this car can experience. And it's going to be more than the gravitational acceleration. That's 1.2 Gs. That's actually impressive. All right, so this is a fast example of how to do problems. Okay, speaking of cute problems, this is extra credit quality, so is this one. Okay, so find this from the handout and just work on it over the weekend. Who knows, this may be your test question. I'm certainly going to design a lab that's going to require this, so you can actually measure the acceleration of your car. I think this is going to be a lab 2 weeks from now. Take-home lab. Okay, let's do a quick review. So where does the external force originate from when we walk? It comes from friction, right? It's surface friction. So action force is going to act on the ground. The reaction force is going to act back on you. That's what it means. It's surface friction. All right, so the next question is, which one comes to a stop sooner? The one with or without the anti-lock brake system? The one with the anti-lock brake system is going to come to a stop sooner because it experiences more friction. All right, so the one with the anti-lock brake system will come to a stop sooner because it does experience more friction. All right, the vehicle without the anti-lock brake system will experience kinetic friction. The one with anti-lock brake system is going to experience static friction because you get to lock up the brakes 18 times per second within this region. So it's going to increase the average static frictional force. That's it. So the possible contributing factors to surface friction is surface area contact, the nature of surface, which is the coefficient of friction, and the normal force. But the contribution of the surface area contact is either marginal or non-existent, so we will just ignore that. So we got static and kinetic frictional forces. How do they differ? Kinetic is sliding friction, static is non-sliding friction. So static frictional force near its maximum value, it's going to be larger than kinetic frictional force. All right, so which one is larger? So static friction is going to be larger than kinetic friction because in the static case, at the verge of skidding, traction is going to be larger. Traction number is going to be larger. Anti-lock brakes lock up the brakes 18 times per second because they're trying to increase the average static frictional force. All right, so that's it. Okay, so we covered the entire chapter right there. Equilibrium. All right, guys, equilibrium, which means that the net force acting on the system is 0. All right, so along the y direction, the net force is going to be 0. N is in the upward direction. W is going to be in the downward direction. And let's take a look at some equilibrium problems. Okay, so we'll take a look at this problem. These are standard problems. I want you guys to actually be able to set these up. Because starting this week, I'm also going to introduce the multiple choice math tests. They're going to be straightforward and simple, but you need to be able to set these up fast and properly. All right, so examples that I'm doing are much more difficult than your multiple choice test questions, but there's stuff in it that's going to help you actually solve these problems. Okay, so the only thing I'm going to do is I'm going to change the weight here to 150 pounds. All right, I'm going to change the weight to 150 pounds. Notice that there's a cable. All right, so this weight is going to induce a force on this cable. It's called tension, and also going to induce a force on this cable. This is known as tension. So these are reaction forces. Tension is a reaction force to weight, and tension is a reaction force to weight. Okay, these are standard physics problems. This is problem number 5 from the handout. All right, so we got this mass. It's going to be 150 pounds. It's going to be supported by 2 cables. One is going to be one of them is going to experience a tension along this direction, force 1, at this angle 60 degrees. The second one is going to experience a tension in this direction. So these are just tension forces. That's what I'm going to say. All right, so we got some tension forces. All right. All right, so the pounds to kilograms. So what are these tension forces? What are these tensions? So force 1 and force 2 in terms of newtons and in terms of pounds. All right, these problems are actually fairly easy to solve because you will follow some kind of a format, the formula, a procedure, a recipe in order to solve these problems. Okay, so you have two unknowns, which means that you will need two formulas to solve for two unknowns. Okay, so you can get two formulas easily. You can sum up the forces on the x direction, and you can also sum up the forces on the y direction. So I'm going to sum up the forces on the x direction. So F1 is going to be in the forward direction. All right, that's positive. F2 is in the forward direction, so that's positive. F1 is in the backward direction, so that's going to be negative. And so cosine of F1 is going to be along the x direction. So x component is going to be cosine of the angle of x F1. All right, so the net force along this direction is going to cause an acceleration. And if it's a static system and it says remains static, which means that there's no acceleration here. So that's going to go to 0 because there's no acceleration, guys. This is a static system. All right, so that's my first equation. So I'm going to get F2 on the left-hand side, which is not that important. So I generated one equation, so I'm happy with that. I'm going to generate my second equation by summing up the forces on the y direction. All right, so F1 is going to have a component along the y direction, so it's going to be the sine of the angle of F1. It's in the opposite direction. W is in the downward direction, which is the same as mg. And so net force on the y direction is going to give you an acceleration on the y direction, but there's no acceleration on the y direction. Okay, so these are static systems, no acceleration. All right, so which means that this equation is going to equal to 0, and this is going to give us a second equation. Okay, so two equations, two unknowns. Okay, so how do you solve a problem like this? You can get F1 from here because you know what W is, which is the weight. And you also know what the angle is, so F1 is solved. If you know what F1 is, you can substitute into this equation, solve for F2. There are like 3 or 4 different ways of doing it. All right, so instead of doing it that way, I'm just going to goof around a little bit because, I mean, there are a million different ways you can use these problems. Okay, as long as you got two equations, if you got two unknowns, you got two equations, that problem is going to solve itself, but you have to do substitutions. So what I'm going to do is I'm going to take this one and divide it by that one. All right, so this one divided by that one. There's no reason for it, but I'll do it anyway. And then sine of the angle divided by the cosine of the angle is going to be, okay, F1s will cancel out, so I can sum for F2. All right, sine over the cosine is going to be the tangent of the angle. Do a back substitution. Not solve for F2. You got the angle, you got the weight. Weight is going to be mg. And then plug the numbers in. All right. And then when you plug the numbers in, we'll get a number in terms of pounds. I think it's going to be 87 pounds. And then now that you know the weight, sum for F1. So the tension is going to be 173 pounds. Okay. There are 3 or 4 different ways of doing it. I end up doing it the long way. It doesn't matter. The only thing you need to know is this. If you got two unknowns, you need two equations. The rest is algebra. I don't care how you do it. The rest is algebra. All right, so we got two unknowns. So you need to figure out what the tensions are on those cables, tension forces. All right, so take a look at the net force on the x direction. So it's going to be 0. It's a static system. It's in equilibrium. Look at the net force on the y direction. So it's going to be 0. The rest of it is just, I don't care how you do the rest. It'll work itself out. So you will have to do a bunch of substitutions. All right, so problem number 6 is once again a standard physics problem. These are incline problems. Okay, you will have to kind of get used to it. So what do we have? We got an incline. This is the 30 degrees. It's going to be measured with respect to that. So we will place this mass on this incline. And then what you need to do is now place the x and y coordinate system. Traditionally, we'll always get the x coordinate system parallel to the surface. So notice that I rotated everything. The weight is acting on it. This thing is static, so static frictional force is going to balance the contribution of this weight. All right, so it wants to move in this direction, but the static frictional force is going to put the brakes on. So static friction is in this direction. So this is your static frictional force. All right, so because it's resting on a surface, it's going to have normal force. All right, so the weight is going to generate a normal force in this direction, and because of its weight, there's going to be friction acting on it. All right, so the mass is 50 pounds. This angle is 30 degrees. There's no acceleration along the x and the y directions because it's a static system. So figure out the static frictional force and figure out the normal force. That's what it says. All right, so put this angle has to be here. This angle that you're looking at through the magic of geometry, this angle is going to go right there. All right, so this angle and that angle, these are the same angles. How is this possible? Guys, it's because these are similar triangles. If you turn this into a similar triangle, that's the way it is. And because this is the sort of stuff I end up learning. I think I was in grammar school, so it's tough to explain this stuff. So it's similar triangles. I don't know what the exact proper terminology is. This angle simply is going to go there. Just remember that. All right. I do my math. Math, for me, it's more of a muscle memory thing. Okay, so I don't do a lot of thinking about it. You look at this, it's going to be right there. Just remember. And the way we do algebra is, once again, it's from almost muscle memory. You don't look for letters in the alphabet whenever you guys are writing a letter or reading somebody's writings. Okay, it has to become part of your muscle memory. Or so whenever you're looking at something, you see what's going on. Anyway, so the next step is take a look at the net force on the x direction. Remember, the x direction is this direction. To the right, it's going to be positive. To the left, it's going to be negative, which means that this frictional force is going to be negative. Also, notice that the weight is coming at an angle, so the weight is going to have an x component in this direction. So this is the opposite over the hypotenuse, so this is going to be the sine of the weight. So it's pointing in the positive direction, so which means that that component is going to be positive. So it's going to be the sine of the angle of the weight that you're looking at. All right, so the net force is what causes acceleration. There's no acceleration along the x direction. All right, so this is our equation number 1. All right, so I'm going to get the unknown on the left-hand side. Okay, so I know m, I know g. All right, so I know the theta. So we already got an expression for the static frictional force. So mass is going to be in terms of that number. G is going to be roughly about 10. Plug the numbers in, it's about 25 pounds. All right, so let's generate the second equation. Take a look at the net force on the y direction. I think I did that a little bit too fast. All right. All right, so let's take a look at the net force on the y direction. What do we have along the y direction? N is in the opposite direction, so that's positive. W is going to have a component along the y direction, so it's going to be the cosine of the angle of W in the negative direction. So N is up, this is going to be positive. W is pointing in the downward direction, so it's going to have a component along that direction, so it's going to be mg cosine of the angle. All right, so that's the acceleration that you're looking at. All right, and then plug the numbers in. You get a number in terms of newtons, expressed in terms of pounds, and then we're done. Okay, once again, let's get back to the basics. 2 unknowns, 2 equations. 2 unknowns, 2 equations. That's all you need. Where do you get your equations from? Sum up the forces on the x and the y directions. If it's a static system, there won't be any acceleration. All right, it's problem number 6. All right, this is an extension of problem number 5. All right, everything is identical. Okay, problem number 6 is, we did problem number 6. Okay. Problem number 7 is an extension of problem number 6. It's the same, problem is the same as the other one, except now you're moving it in the upward direction at a constant speed. All right, so here's your mass, and you apply a force on it in the upward direction. All right, so there's a tension, there's a rope or something, some kind of a pull in the upward direction. It's going to generate a tension in the upward direction. So it's going to generate a motion in the upward direction. So this is your velocity. And then you're pulling it in the upward direction at a constant speed, so it's experiencing surface friction. So that's your kinetic friction. So I'm going to place my coordinate system right at that point. This is going to be the center of mass. All right, so x coordinate system, the y coordinate system. And I'm also going to place the other forces. W is coming in the downward direction, and then it's going to cause, there's a surface force, normal force going up. Okay, so that's it. So what do we have? We got tension, we got the weight, we got the normal force, we got the frictional force. We got 4 forces, guys. We got 4 forces. All right, so here's the background. So we know the mass, we know the angle. It's moving at 20 miles per hour. So what is the frictional force? What is the tension? What is the normal force? Given weight. All right, so this is going to require, we got 3 equations. Okay, we got 3 unknowns, which means that we need to have 3 equations to solve this problem. All right, so how do we do that? So this thing is moving along the x direction at 20 miles per hour, which means that there's no acceleration, guys. This is once again a static case. It's moving at constant speed, 20 miles per hour. All right, so there's a conversion here, which is not important because I'm not going to use this number. So only thing I have to do is generate 3 equations to solve for 3 unknowns. I'm going to sum up the net force along the x direction. All right, so this is the kinetic frictional forces in the positive direction. Tension is in the negative x direction. W is going to have a component along the x direction, along the positive x direction. So this is the opposite of the hypotenuse. So this is going to give you the sine of the angle for W. So instead of using W, I'm using mg. There's no acceleration along the x direction. So this is my first formula. All right, I'm going to keep my knowns on the right-hand side, unknowns on the left-hand side. I don't like the negative here, so I multiply both sides by negative and then move the terms around. Okay, so this is good enough. So this is my equation number one that allowed me to generate one formula. So I was able to generate my first equation. The second equation, I'm going to be able to generate by looking at the forces along the y direction. So what do we have along the y direction? We got n along the y direction and w as a component along the y direction in the downward direction. So it's going to be n minus w, and this is adjacent over the hypotenuse. So it's going to be w cosine of the angle of w is what you're looking at. Cosine of the angle of w. Yeah. Okay, cool. All right. So there's no acceleration on the y direction. This is my second equation. Okay. Now I will stop. What am I looking for? I'm looking for n, I'm looking for tension, and I'm looking for the kinetic frictional force. Okay. From here, I can get n. All right. At least this is going to surrender. Okay. So we will be able to only solve for n at this point because only got one unknown here. So normal force is going to be about 43 pounds. All right. It's going to be 43 pounds. All right. We still have two unknowns here. All right. So now we have to come up with one more equation for this one. We have an equation for the frictional force. It's the kinetic frictional force. So except for us to be able to solve this problem, we need to know the coefficient of friction for the kinetic frictional force. Coefficient of friction for the kinetic frictional force. I'm looking around. I don't see the coefficient of friction for the kinetic frictional force. There's no way you can figure that out because it's an experimental number. So I'm going to give you this. So this is just an assumption. I don't know what the actual number is, but one of the future labs, you guys will actually figure out. I'll show you how to measure something like this. Let's make the assumption that it's 0.45. All right. So with that assumption in mind, I'm able to generate a number for this one. And then, which means that I know what the frictional force is. If I know what the frictional force is, one thing you have to do is solve this for t. Bum, bum, bum. All right, so everything is done. So this is going to be about, I don't know what number we got there. That was actually a cute little number. It's 45 pounds. Okay. So the original weight is going to be 50 pounds. Normal force is going to be 45 pounds or whatever. So things are going to work out. All right, here's the last problem. We got like 6 minutes to go. This one is an impact problem. All right, so problem number 10 is an impact problem. I like this one. All right, so we got a person who's going to be jumping from the second floor of a house. It's going to be 20 feet up. All right, so a person is going to go in a free fall. And then using his torso, he's going to slow himself down. All right, so using his torso, he's going to slow himself down. So he's going to bend his knees. He's using his torso. I mean, using his legs, he's going to bend his legs basically a distance of 2 feet. So I'm going to make this y prime. All right, so within a distance of 2 feet, this guy's going to come to a stop. He's going to jump, undergo free fall, and then as soon as he touches down, he's going to bend his knees, and within a distance of 2 feet, he will slow down. All right, so this is the mass of his torso. All right, so the question is, how fast is this person moving at the moment he touches the ground? So what is his final free fall speed? And what is the amount of force required for him to come to a stop? All right, so what is the amount of force required for him to come to a stop? Okay. All right, so he jumps 20 feet, uses his legs to slow himself down. He's going to be able to bend his knees about 2 feet of distance. He's going to gain that amount of distance while come to a stop. What is his final free fall speed? And what is the net force acting on him while he's coming to a stop in terms of newtons and pounds? All right, so what I'm going to do, I'm just going to grab every single formula relevant to this problem. Okay, so there's going to be an impact force, there's going to be an acceleration. Every single formula related to acceleration is here. He's going to jump, so we need the free fall formulas. All right, so this is my toolbox. So I placed everything on the side. I'm listing everything. And then I finished up the conversions. All right, so the first thing is, this is the distance that he falls. So what is his final speed? It's free fall. He jumps. Initial speed is going to be 0. We don't know the time, but we know the distance. So these two equations are not relevant. The only thing that you can use is the last one. All right, so for the final speed, it's going to be about 25 miles per hour. So this person is going to hit the ground at 25 miles per hour. And down, he's going to bend his knees. All right, so at that point, he's going to bend his knees for about 2 feet. All right, his body will go through jerking motion, but the impact time is not available. Impact time is not available, so you cannot use the average acceleration formula, which means that we have to do an estimate. The estimate that we will get to use is going to require us, we have to make the assumption that the acceleration is constant. So we have to pick our formula. Time is not available, so these two are out of the question. So the only one that we can actually use is this one. All right, so this x that you're looking at is going to be the same as y prime. So that's the distance within which it's going to come to a stop while he's bending his knees. So the final speed in free fall becomes the initial speed in impact. All right, so the final free fall speed becomes the initial speed in impact. It'll come to a stop within a distance of 2 feet. So what is the acceleration? So what that means is we need to solve this for acceleration. And we have to use this formula, except instead of x, we will use y prime. All right, that's it. All right, so solve for a. All right, so the algebra is going to take care of itself, and then do a back substitution. Just out of curiosity, I wanted to know what the acceleration was. The acceleration is 3g's. That's expected at 25 miles per hour. If you're going to bang your knees, that's easily survivable. And then you do a back substitution. This formula is going to go there. And then plug the numbers in, and this time it's going to be about 300 pounds, I think. Yeah.